when you are not looking, and they have new puppies coming up. Okay? For example, there's a really cute black and white puppy. At which point when you pick up a puppy, it can be either black or white or any color in the rainbow. That's your fuzzy logic. You have to understand this distinction. You see what I'm saying? In probabilistic reasoning, the proposition is either true or false in a given word. It's not 0.7 true in the given word. There is no such thing. Fuzzy logic, on the other hand, says in any given word, a complete word, it's only 0.7 true. So that's like saying this little puppy is actually kind of maybe 70% white. However. Okay? So that's the difference between fuzzy logic and probabilistic logic. Fuzzy logic basically makes things truth functional, makes it easier to do reasoning. That's why people like it. That's why washing machines use it. But washing machines don't do chains of reasoning. They'll just do one level reasoning. And if you just do one level reasoning, you can't fall back. You can't be bad. And in fact, there's a nice paper called Paradoxical Success on the paradoxical success of fuzzy logic. And that basically points out that the problems with logic, fuzzy logic, will start showing up when you do chains of reasoning. To have circularity, you should do more than one inference. Otherwise, how are you going to get circuit? This is what I'm saying. Mostly, your washing machine is going to say, time to stop revolving. And that one level, you can't tell the difference, whether or not there is a time. So this is enough. We would not care about fuzzy logic anymore in this class. Instead, we care about probabilistic logic. And what I want to do is introduce that, and then basically next class onwards, and we extend it to today as well as next class onwards, we'll be doing probabilistic logic. So here's the deal. Yes?
So can most of these issues be solved by having some kind of a thresholding functions? Like
they can all be solved by finally doing probabilistic. But you can invent it differently and call it no probability. The reason I told you this is because history is full of reinventing probability theory. There's even one more called Dempster-Shafer theory. That's not as bad, but nobody uses it either. Okay? The only thing that sort of stood the test of time is probability theory, as of now. Okay? So, let's do the probability theory. Well, suppose we do know the likelihood of each. So first of all, let's look at this and understand. Probabilistic propositional logic assumes that the world is made up of statements that are either true or false. No in between. So either it's a white or a black puppy. No in between. However, when you are looking at 100 words, in 17 of them it may be white and the other it might be black. That's the likelihood. You see what I'm saying? That's what probabilistic reasoning does. So probabilistic reasoning is actually truth functional only for a single word. In a given word, it's either true or false. But combining likelihoods essentially involves set theoretic reasoning, which is why probability reasoning actually, in fact, most of the problems that people have about how the world works, whenever there's something which says paradox, it's about probabilistic reasoning. I mentioned already to you, how many of you looked up Simpson's paradox? Yeah, you should look up these things. These are things that you would assume intuitively, quote unquote intuitively, that world will work one way, but the numbers tell you the other way, and in fact the world works according to the numbers tell you. In fact, the whole idea of people being predictably irrational is all because they don't know how to deal with uncertainty correctly, mentally speaking. But one of the beauties of civilization is we don't have to be stuck with the way we reason in our head. We can write programs, we can write theories that have properties. You see what I'm saying? Okay. So suppose we know the likelihood of each of the propositional words, which we will find out. In essence, what you're saying in probability reasoning is you still have these truth tables. And in every row, if you have PQR, let's say, in every row P is true or false. The only difference is there is an extra column called truth of the word, from the likelihood of the word. And they will have some numbers. And all these numbers are between 0, P less than or equal to 1, such that the sum of all Pi is equal to 1. This is what is called joint probability distribution. Just as in propositional logic, if I give you the truth table, you will be able to answer any query. You just did it faster by doing all these additional things like, mod exponents, etc. But you know how to do just first principles, you can do it just from the truth tables. So what's the truth table version for probabilistic reasoning? The joint distribution. So in fact, the idea in understanding probability theory is if I can somehow take whatever I know and convert it to a joint distribution, then I can solve any probabilistic reasoning problem. Do you see what I'm saying? And that's what you did in logic too. Let's say I'll say P implies Q and P and Q. Then you made it into a truth table where those things are, evaluated. And then with respect to that, you can compute a table. Okay? So we will go into this again by next class as well as part of today's class. Joint probability distribution is all you ever needed to be able to answer any probability reasoning. The problem is, then you can just use standard rules of probability to compute likelihood of all pairs. So this is the only thing we ever needed. So in the case of Perl examples, we just need the probability distribution for BEAJM. That means there would be a 32 row table. Because there are 5 variables, they are Boolean, there will be a 32 row table. And you need to give numbers for each of those rows, such that those numbers add up to 1. And you're not allowed to use negative numbers. They all should be less between 0 and 1. This is basically what specifying knowledge is. 2 more things before you can go off. So if the joint distribution is sufficient for reasoning, then where is the domain knowledge coming from? So the question is, basically the domain knowledge about a world essentially will sort of try to tell you approximately these things like, B kind of implies, burglary kind of implies alarm, earthquake kind of implies alarm. Okay? You write it. Now you take a deep breath. That's a baseline. Okay? So, in essence, it looks as if there is a link from burglary to alarm, an earthquake to alarm. These arrows are directional, they are arrows, they're directional. And then alarm to John calls, alarm to Mary calls. Except they are not written as these implications. This structure essentially tells you the approximate connections between the variables that you had in the propositional logic case. This is what you more or less still believe, that burglaries typically lead to alarms, earthquakes also typically lead to alarms. Alarms typically involve, push John to call, alarms typically push Mary to call. This is the qualitative connection between the variables. And now I need the numbers. And the numbers I put there, in essence, when unrolled, will become a 32 truth table with 32 numbers. In particular, for the first part of the class, before the extended period, I want you to understand at least this much, that you have just written this. And all you need to know is to specify this. To specify a Bayes network, you sort of have to specify the topology of the network, which is what we did just now. You get the topology from your understanding of the causality of the domain. And in general, you are better off putting the links in the causal direction, but it's not required at all. Okay? And having put the topology, whatever topology you put, then what I will be doing is for every node, above that node, with respect to that node, I need to provide a table of probabilities. That would be what's called a conditional probability table. And what it says is for every node, tell me the probability distribution of that node given the different values its immediate parents can take. That's it. Okay? So, for burglary, I need to get the probability distribution of burglary given its immediate parents. It has no parents. So I just give probability of burglary, probability of not burglary. But then I'm smart. I realize that if I give you probability of burglary, 1 minus that is the probability of not burglary. So I just give one number. Similarly for the earthquake, I gave one number. In fact, the numbers in the next slide, the numbers are bigger. Okay? And then for alarm, I need to give probability alarm is true, given burglary is true, earthquake is true. Burglary is true, earthquake is false. Burglary is false, earthquake is true. Burglary is false, earthquake is false. For each of these, I need to put numbers. And if you put these numbers, of course, then I know the not A version of these numbers. Right? Okay? So, that's all I need to do. And then, of course, for this guy, John calls, notice that alarm has two parents. So, the number of probabilities you need to give at a node is, for a Boolean variable scenario, it will be 2 power k, where k is the number of parents. You see what I'm saying? Okay? And so here John calls, probability John calling is only connected to alarm. So I just need to give probability of John calling given alarm is true, given alarm is false. Just a second. And probability of Mary calling given alarm is true, given alarm is false. Here's the thing. Given these numbers, I can uniquely construct a 32-row table where basically corresponding to John, the 32 different worlds of John calling and the 5 variables, 2 power 5, and the likelihood for each of them. Which means given this, I can get the joint distribution. This is actually capturing the joint distribution. But then, why not just give that? The reason is, if I gave that, I would need to give you 32 numbers. Well, actually 31 numbers. Because if I give you 31 numbers, you can stop and say, Rao, I can add them all up. 1 minus that will be the 32nd number. Together. Right? How many numbers do I have to give to do this? Add them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Instead of 32, I gave 10. And I still have a joint distribution. Here's my question. What do you think you should do to this network such that I can give even fewer numbers?
We can find a conditional probability.
No. What do you think you can do to this network? Remember the following. The number of numbers are dependent on the number of arrows and the number of parents. What is the best case scenario? There are no parents. Nobody is connected to anybody. It's an independent world. You see what I'm saying? It turns out that there's a beautiful Bayes network which is like this. BEAJM. No damn connections. Right? How many numbers do you need to give to specify this? 5. So for n random variables, if you assume that nothing is connected to anything, everything is independent, in instead of giving 2 power n numbers here, you can give n numbers here. How many times do people doing probability reasoning say, let's just assume independence? Why? This is the same reason why people look for lines, because life is easy. The last thing before I shift to the later part is that in essence you will understand when you come back next class that what the Bayes network is capturing is a set of conditional independence assertions. In essence, by putting these arrows, you are saying alarm is sort of dependent on burglary and earthquake, and John calls and Berry calls is dependent on alarm. And that's what you are giving as the knowledge. That's the topology. After the topology, you go get the numbers. So we'll stop for people who have to leave, and then I will continue on the Tell me one thing. Okay. Let's continue. Let's continue. It's fun stuff. Okay. So actually, you guys will be in much better position next class because you understand this, not this guy. So basically, you have this as a network, and the network is somehow the topology of the network is capturing, in essence, some sort of dependency relations. It's sort of trying to tell you what is independent of what. We'll try to figure out how that is done later. Now, the only question that I didn't tell you is if I give this, I said there is a way of getting the joint distribution. Right? Remember that if I can ever compute the joint distribution, then I know the problem is solved. Right? Because any probabilistic query whatsoever can be answered if you know the joint distribution. Maybe it's not the most efficient way, but it's answerable that way. You see what I'm saying? So to prove that this captures a way of representing probability distributions, you just have to show how to go from this to numbers here. Right? Let me do the following way. Actually look at this happy network. It's also a network, it's also a Bayes network. Right? It's a Bayes network where nothing is connected to anything. Right? Okay? And so it will have 5 numbers. Probability of B, probability of E, probability of A, probability of J, probability of N. That's the only things it will have. Here's my question. Suppose I have to fill up an entry here, which is B to not E, not A, J, not M. That will be one of the entries. I just need the number for that. I can compute that. You see what I'm saying? How do I do this? Basically, let's, I can just say it's probability of B times 1 minus probability of E times 1 minus probability of A times probability of J times 1 minus probability of F. Whip up your calculator, put the numbers in, you're done. In general, this is why people like independence. All things, nothing is connected to anything. Okay, in that case, you only need n numbers, where n are the number of Boolean variables, and then you can just get all the 32 power n numbers. just magically can produce them. Nice, right? The only question then is, how do I do it for this more general case? So how would I have computed the same thing, probability B, not E, not A, J, not M, here? All I will basically say is start with probability of B, this is 0.01 for this basically. I'll just say 0.01 for the probability of B, burglary, times probability of not E. Go basically from top to bottom in the topological order. I'll explain to you why this works later, but just go top to bottom in the topological order. Okay? So times 1 minus 0.002. At this point, I'll come to alarm. By the time of alarm, I know whether burglary is true. I already know that burglary is supposed to be true, earthquake is supposed to be false. So I just look at the correct row, T and F. And it says 0.94. Just write that number. Okay? Then I need to get the John Calls guy. John Calls, by this time, according to, oh sorry, it should not be 0.94 because I'm looking for not here. Where should I go? Okay. It should be 1 minus 0.94. Right? Because I'm looking for not A given B and not E. And B and not E is 0.94 for A. For not A, it will be 1 minus that. So that will be 1 minus 0.94 up to that. And then I have given not A, what's the probability J? That's what's the likelihood that John will just call to say hello, even though there's no alarm going off. Right? So I just look it up. What is the probability that John is calling even though there is no alarm? John is sort of a fire-weather friend, right? So you only call when there is fire or alarm, I guess. So if it's not, if there's no major problem, the probability that he'll call is 0.05. Okay? So I multiply that. And then I want not Mary calling. John should call, but Mary shouldn't be calling. But by the time I came to Mary calling, I know all its parents. The advantage of traveling in the topological sort, okay, is you would come to a node after having seen its immediate parents. Because that's the definition of topological sort. Right? So you would always be able to read up the numbers from the table. Like right in front of you, there in the table. You see what I'm saying? So how do you read up not M? I need not M given not A because the parent is not A. So not M given not A would be not A, Mary calling when there is no alarm is 0.01. Mary calling it is 0.01. Mary not calling is 1 minus 0.01. So Mary is even more of a not calling person. Even call more, but not calling not. Anyway, so that's it. Then you whip up your calculator, multiply the numbers, you got the number. Do you see that you can do this for every one of these rows? Do you really understand that if I were to give you the joint distribution, I can answer any probabilistic query? Because if I give you joint distribution and you wanted to know what is probability of A, then you will add up all the numbers corresponding to the rows where A is true. That's called marginalization. You see what I'm saying? And similarly, if I want to know what is the probability of A and B, I'll add up all the rows where A and B are both true. The other thing would be A given B. But we know that probability of A given B is nothing but probability of A and B by probability of B when B is not equal to 0. Right? That's the definition of conditional probability. So I can compute PA given B2. What else can you ask? You can ask the truth of A and B, you can ask the truth of A or B. You can ask the truth, you can ask the truth of A and B, you can ask the truth of A given B. The only other thing left is A or B. The beauty is that you guys know the answer for that too, right? Probability of A or B is probability of A plus probability of B minus probability of A and B. Except, it turns out this is a controversial axiom. You should read the textbook. It turns out you can give semantics for probability theory without actually specifically taking the definition of probability A or B to be this. You just always mark it up, in your grade school, but you didn't quite know. But there were raging battles in the probability community. And there's a beautiful write-up in the textbook which basically says that a guy called Definity, here's our definitive answer. What Definity said is fine, you're welcome to use a different formula for ARP. But if you use any formula other than this, I can set up a betting game where all your money will be mine. People may or may not care about theoretical consistency. Losing money, no good. You see what I'm saying? So actually you should read this. It's a beautiful background as to why ARP is described this way. It turns out that if you do it in any other way, you can essentially set up a betting game where bozos who believe the other way will lose all their money. And so evolution will slowly take care of it. Right? See what I'm saying? Okay, so given that I can do ARB, A and B, A given B, I know that given a joint distribution, I can get any probability value, any probabilistic value. Typically, the kind of probabilistic queries that you will ask is, what is the distribution of a particular random variable given the evidence that this variable has this value, this variable has this value, this variable has this value. So typically I might ask, what's the probability of this probability distribution of alarm? What's the probability distribution of alarm given burglary is true, earthquake is true, John Calls is true, Mary Calls is true? You see what I'm saying? And so if I want to run and solve that, so what I'm asking here is probability distribution of alarm given B, E, J, M is what I'm asking for, right? And that's nothing but P, A, B, E, J, M by P, B, E, M. This guy lives in the rows. One of the rows is this. This guy is just the summation of the rows A and not A, with the rest of the values being the same. That's how you will compute the value for alarm being true, and I can also compute probability not A version. Then I will get the distribution. Typically you ask for the distribution. Okay? So what is actually happening here under the hood is that the networks capture a particular form of conditional independence. What they say is the following thing. Let me see if I can go to the next one. Yeah. Okay, I can write it here. The networks capture have particular kind of conditional independence. Okay, which is that the probability of alarm, so here we go, probability of John Calls given alarm, burglary and earthquake is the same as probability of John calling given alarm. That's it. You more or less use that, right? Because when you are looking for John Calls, we only looked at this table, John Calls given the alarm. But by that time, actually, burglary and earthquake were having some values. Berkeley is true, earthquake is not true. I don't care. In fact, what happens in Bayes networks is the immediate parents shield you from the evil influence of your ancestors. That's true. They throw a blanket over you that will shield you from the ghosts of the ancestors. But they don't shield you from your descendants. Do you understand what I'm saying? Okay? So all that Bayes networks say is probability of a node given set of all its ancestors is the same as probability of that node given just its immediate parents. That's it. And that's what we wound up using in computing these numbers. You see what I'm saying? Okay? Now, because of that, basically, and once that is, once you have the, so in trying to write this network, you essentially have to see what should be, once you put a, so basically if you really believe that when earthquake occurs, Mary calling is not just dependent on alarm going off, but Mary also has a separate earthquake line to you. Suppose you believe this. That network doesn't capture that. So if you want to believe it, you should have put a link from earthquake to Mary. So that's what giving the topology of the network means. Topology of the network is telling what you know about the domain. See what I'm saying? Okay? And so bunch of things we did here. For example, this is a normal probabilistic network. This is a network that I just showed. We sort of you agreed this is a reasonable kind of connections. Okay? And this is a network where I assumed everything is independent of everything. That winds up having the least number of numbers needed to specify the network. Okay? Now, what is the worst case network that you can think of? Because you thought of the best case network, which is this. What? How does that happen when you have arrows with directions? It is complete acyclic graph. It's not just a complete graph, because you can't have circularity in the arrows. You see what I'm saying? So the worst case scenario would be you put in the first node, the second node will have a link from the first node, the third node will have a link from the first and the second node, the fourth node will have the link from the first, second, third nodes, the fifth node will have a link from all four nodes. In which case, it will be 2 power 4